Welcome to Pragmatic Approaches to Architecture Metrics. So today we'll start, as we do many architecture talks, with a famous quote. Today's quote comes from a management consultant and author named Peter Drucker, and it says, "What gets measured gets managed." Of course, fits the conference theme, which is metrics. I hear that in my line of work a lot. Usually comes with requests for metrics. Well, turns out that Drucker never actually said that. That's according to the Drucker Institute. And some digging revealed an origin for this quote. Turns out it actually comes from a guy named Simon Kalkin. He was reviewing a paper titled Dysfunctional Consequences of Performance Measurements. And his summary of the paper is the quote that you see here. What gets measured gets managed, even when it's pointless to measure and manage it, and even when it harms the purpose of organization to do so. So as you can see, very different take. And it's on a paper that was written many years ago and is expressing some healthy skepticism about metric-obsessed culture. So what does that mean? Not everything that matters can be measured. Not everything that can be measured matters. We've seen plenty of bad metrics out there. Just think of a number of lines of code as a metric of engineering productivity or even architectural complexity. How easy that metric can be taken out of context, misinterpreted, gamed. So today we're going to talk about what it means to measure your architecture, what matters and what doesn't, and how to stay pragmatic in your approaches. We already had a really lovely introduction, so we'll just be brief here. We're both somewhat of a metric skeptic, so it made it for a very interesting challenge to put our lived experience into a structured approach. We've seen metrics lead to suboptimal outcomes, to unintended consequences, and we wanted to identify what matters, how to measure it, assuming that we can measure it at all. My name is Sonya Natanzon, and today I will present to you a strategic business-focused architecture metrics. Vlad?
Hey, I'm Vlad, and I don't trust software design metrics, okay? I'm going to rant about why I don't trust them, and hopefully I will give you a different approach to evaluate complexity of code bases.
All right, so some assumptions. First, everybody wants to know if they're successful, including software architects. We want to know if our architecture is working, and the business that's paying us the big bucks to design that architecture wants to know how well it's working for the business. Second, everybody wants quantitative measures. Nobody likes to have qualitative or go on feelings. I feel this is working pretty well for me. Certainly, it's a lot harder to argue that against, thanks to our new architecture, our customers' pages now load in half a second or less. Okay. Last but not least, software architecture is difficult to measure. Why is that? Well, it's difficult to define what it is in the first place, this nebulous software architecture. And success of the architecture is in the long-term goals. It's rarely in the short-term gains. So if today those customer pages are loading in half a second or less, will they still do that in 2 years when those customers have a lot more data? Will it even matter in 2 years? So I just said that software architecture is difficult to define, but there is a widely used definition out there, which brings us to the second famous quote of the day. And that one is by Ralph Johnson. Architecture is about important stuff, whatever that is. It's a cute definition. Many people use it. But as definitions go, still really kind of nebulous. What is important to software architecture? We're going to want to know what that is, and we're going to want to measure that thing. We also know axiomatically that architecture's purpose is to support business goals. Without solving a business problem, Mark just had a lovely example of student testing, architecture becomes kind of an academic exercise. All of your architectural decisions, all of your trade-offs, they have an objective, and that's usually set by the business problem that you're solving. So if architecture is about important stuff, and architecture's purpose is to support the business goals, it stands to reason that what's important to architecture is whatever that thing is that supports the business goals. Okay, so we're now getting to some better definition out there. So to know what to measure, Let's identify what qualities of architecture are important to support the business, and let's see if we can measure them. But are there really universal qualities that are important to all businesses without really knowing what the business is? Is the same thing important to healthcare as to fintech or online ads? And it's that thing that we're going to want to measure? Turns out that there is, or there are two of them, and I sum them up in two words: evolution and scale. Regardless of what the business is, its ability to change and evolve and its capacity to scale out are critical to its survival and need to be supported by software architecture. And I can show it with product evolution. So this would be a typical path of a successful product evolution. And I say successful because if the product fails to find its audience, find its market niche, it dies. And if the company is sufficiently young and maybe can't change along with it, it's going to die right along with that product. So we intuitively know what's important at those early stages. It's being able to make quick changes so that we can test the product out in the market and find a good niche. Now, as everything on PowerPoint does, this is lovely and linear, but in order to get to adoption, sometimes these products and these businesses take some pretty drastic turns. In fact, Vlad, you have a good example of a startup that made a lot of changes.
Yeah, that's true. So a few years ago, I was working for a startup company, and when we were just getting started, well, we didn't really know what problem we really want to solve, let alone we didn't know the solution that we are going to provide to our customers. So initially we were like a general online marketing company, then we wanted to specialize in online gaming, and afterwards a few other industries, and eventually we ended up being a fintech company. So during the first 1 or 2 years of the company, our business domain has changed like 4 or 5 times.
Wow, that is a lot of changes and some pretty dramatic ones. So that's early development. Later on, when the product is adopted by the market, hopefully has a loyal customer base, business is going to want to scale out and fulfill that unmet need. And that could mean larger quantity, faster production, lower cost, fewer defects, any combination of those things. So if we look closely, both evolution and scale are different aspects of business's ability to change. And since software architecture needs to support the business, it needs to be able to change right along with the business. So it's that ability to change that we will want to measure. It's that common thread to all businesses out there. We can try and represent this on a graph. And the two axes to this graph are change frequency and change effectiveness. The curve is what I would call a product maturity curve, and it starts to differentiate what's important at different stages. Early on, it's a lot of fast changes, hopefully low effort, but they will miss the mark sometimes. And that's okay. Product's young, we're testing it out, maybe the change is not super effective, we can just make another one. Later on, when product is stable, there's customers with expectation of value, with expectation of quality, reliability. Changes are going to take more effort. They're going to become less frequent, but they're going to be a lot more targeted and precise, focusing on value to the customer and keeping disruption to them very low. The company that I currently work for actually is going through exactly that type of transformation. What I measured as success, what mattered a year ago, which was fast product launches, is really no longer good enough. It doesn't matter anymore. It basically went the way of the dodo. It yielded to operational excellence, rapid scale. So as business evolves, our metrics, the focus of our metrics, has to evolve as well. What's interesting is we're still measuring the same thing. It's frequency of changes and effectiveness of changes, but the focus is no longer on frequency, it is fully on effectiveness, which is value to customer and quality. I'd like to introduce these 4 metrics to you. And first one is change lead time, sometimes it's called cycle time. Second one is deployment frequency. Next one is change failure rate, sometimes called change fail percentage, and mean time to recovery or restore. If these look familiar, it's probably because you read the Accelerate book where they were originally introduced. And even though these metrics originated from the world of DevOps, we can easily take them and apply them to software architecture. If we think of these as architectural qualities that support our two vectors of change, we can see them as individual measurable qualities under each umbrella. So change frequency encompasses change lead time and deployment frequency. What's the total it takes for us to make a change? Do we need to collect a bunch of them in order to do a production deployment? And under change effectiveness, what is the failure rate? Failure rate here could be anything from just basic system downtime to change failing to bring value to users. Oh, too far. So there's a lot of nuance to these seemingly simple metrics. I want to talk about how we measure them, and we measure and do it in a very simple, pragmatic way. These guidelines are focused on data collection, on analysis, rather than tooling, automation, algorithms, and really not taking away from your primary objective, which is having an architecture that supports your business. So your first responsibility as an architect is to define your measurements. What constitutes a change for you? Where does it start? Not a simple question. Does it start when product manager dreams up a feature? From the moment when it gets approved? Maybe from a refined user story or from an engineer who's starting to code that feature. Where does it end? Is it production deployment? Is it feature flag being turned on? Is it first beta user or a real user starting to use it? There's lots of definition there. Same with failure. What constitutes failure? Is it downtime? Not always. We run at 4, 5 nines, and yet somehow some things are still considered a failure. Is it many, many support tickets that might show up after a deployment? So all of these definitions are foundational to what you do next. Please make sure to check them with your stakeholders. Make sure that your definition of success and their definition of success is aligned. And write them down, because if you don't, somebody else will, and they will look different than what you think they are. Collect a bunch of data points. You don't always know initially what might be useful, what's going to be important. If you can collect data in a low-friction way, such as your ticketing system for implementation or support, great. You can adjust those systems to collect additional data points. They're very convenient to extract analytics from. And you likely go through a few rounds of iteration to find out what in fact is useful. Architecture metrics get difficult because of these very definitions that I just talked about. Automating them can be even harder. Don't invest too early, at least not until you know what you're automating. And for the systems that are already automated, like CI/CD pipeline as a source of your deployment frequency metric, the next point is going to be super important. Don't show the raw numbers without contextualizing output. What I learned over time is numbers never ever speak for themselves. They require a bit of a voiceover. Simple example, employee satisfaction survey. We do those twice a year, January and July. In January, everything looks great, everybody's happy. In July, it looks like everybody's ready to quit. Why? Well, it was January. We just came back from holidays. Everybody's well rested. We're maybe want to get out of a family circle and do some work. And then July comes. We just worked hard for 6 months, maybe had a death march of a product launch and ready to go for a summer holiday. So yeah, context. If maybe we did those in April and October, then the company would look pretty even through time. So if you're showing outputs, make sure you have the definitions of your metrics right next to them. Make sure you have methods for collection available and any context and interpretation that you need to put on them. Deployment frequency, always a fun one. If you have frequent deployments, it might look great, like you're delivering value to customer all the time. Might also be that your deployments keep breaking things and you keep needing patches, so interpretation matters. All right, so these were some really simple practical ways of measuring the success of your architecture, specifically its ability to change on these two vectors of frequency and effectiveness. Of course, nothing's ever so simple, and a word of caution that I'd like to give you that is called Goodhart's Law. So this gentleman was talking about British finance policy, but he said that any observed statistical irregularity will tend to collapse if pressure is put upon it for control purposes. More simply put, the quote that you see is, when a measure becomes a target, it ceases to be a good measure. Effectively, what this is the law of unintended consequences that occurs when you're trying to target a measure. And the COBRA here is the story of COBRA effect, which you may know it's a great illustration of unintended consequences. Way back in the day, British government was concerned about a bunch of cobras around Delhi. And so they decided to incentivize the citizens to bring them in for a reward to reduce their numbers. So what did they start doing? They started breeding cobras. Well, turn them in for a reward. British government did not like it, got the wind of it, said no more rewards. So what did the breeders do? They let all the cobras out in the wild. So Delhi ended up with a lot more cobras than it started with. Unintended consequences. What are some of the metrics that I've seen lead to unintended consequences? Code coverage, my favorite. We always put on 60, 70, 80, 100%? Anybody has 100%? Yeah, it's never 100%. So when you have, say, your 60 or 70%, and you need to hit that target as an engineer, what do? You start with the simple ones. Your getters, your setters, maybe some algorithms. You leave all of the really complex business logic in that 30% that you're not covering, and that completely defeats the purpose of that metric. Bugs found, that's another fun one. Incentivizes test engineers to log anything, including typos, because they want to hit that metric, and completely disincentivizes collaboration. They stop talking to each other, even though a lot of these things can be resolved with a very quick and simple conversation. Deployment frequency, when that becomes a goal, we start doing little bitty engineering deployments that don't necessarily bring value to customer, and that's an ultimate arbiter of the value. So it looks like we're doing a lot, but is it meaningful to the end goal? Maybe, maybe not. And of course, crash rate is another fun one that requires a lot of context to focus on the right problem rather than a simple one. So not everything that can be measured matters. All right, so there's one other metric that underlies both change frequency and change effectiveness, and that is change cost. What is the total cost? In opportunity, in time, in money, in engineering hours, in revenue, in customers, in maybe lost opportunity when we could have been solving a more important problem. If we were to put change cost on our graph, we can express it as a linear vector that is proportional to either change effectiveness or change frequency. In order to make fast changes, idea to deployment, we're going to need to invest. More engineers, better tooling, better automation, and so on. For more effective changes, we're still going to need to invest, though differently. Maybe better UX design, maybe more regression tests, etc. So ability to make more frequent changes costs more, and ability to make more effective changes costs more. Change cost is not an independent metric. It is a sum total of all four metrics. And as an architect, you get this question asked a lot of you. What does the change cost? Even better question is, how do you keep that cost down? And how do we do that? With trade-offs. We figure out what is the more important metric, we focus on it, and likely take away from another one. Trade-offs are a hallmark of software architecture, and Product development is an example of trade-offs. Early on, we focus on change frequency at the cost of effectiveness. Later on, change effectiveness at the cost of frequency. And by doing that trade-off, what we're doing is we're keeping that cost linear and proportional to the more important metric. Of course, our business would love to have both. They would love to have fast changes. They would also like to have very effective changes. But that is now a cost of changeability, and it's no longer linear. It is super linear to both of those metrics. And that cost can be prohibitive or even unnecessary. Why would you want to invest in something, in a product that is mature, maybe doesn't need to change as much, maybe your customers don't love frequent changes and it takes a lot of change management, or maybe it's regulated and just can't change all that often. Last but not least, each of these metrics have an important common factor that directly affects change cost. And that common factor is complexity. So that is your keystone. It's the biggest predictor of how your metrics will perform. It resists everything. Complexity resists everything. Makes cycle time longer, increases failure rate, makes recovery more challenging. And complexity tends to be very contextual and multi-layered. It's business versus technical, it's essential versus accidental, it's complexity of software versus complexity of operating the software. It has to go somewhere. Since complexity resists our four metrics, all four of these factor in our cost of change, then the cost of change becomes proportional to complexity of that change. And we kind of know this already. The more complex something is, the harder it is to change, the more likely it is to break, and the more difficult it is to bring back to a normal state. You can get a good idea of how your metrics will perform if you understand complexity behind them. A lot has been said about complexity, probably none better than my co-presenter, who is literally writing a book that addresses the subject, at least in part. We know what complexity is kind of intuitively. It is the software that doesn't fit in our heads. But as I said before, nobody likes to go on qualitative or feelings. And Vlad will take us through the pragmatic approaches for measuring complexity.
Thank you, Sonya. And just as Sonya started with definitions, I want to do the same. And I want to ask, what is this thing that we call complexity, you know? What is this beast that we are so scared of? And a cute definition comes from one of my heroes, a physicist named Geoffrey West, and in his book he said, well, complexity is something that you know it when you see it. Now, it's intuitive, it's cute, true, but we need something more practical to work with to evaluate complexity of code bases. So let's borrow one from the Khononov framework. Anybody here familiar with Khononov? Few hands? Cool. So for the rest of you, according to this model, Khononov, complexity is defined as the relationship between an action and its outcome. Or more specifically, how predictable is the outcome of some action. So if you're doing something and you know exactly what's going to be the result of that action, that's not complexity, that's something simple. If, on the other hand, you don't know what's going to happen, but you can easily find an expert that does know, that's not complexity as well. That's something that is complicated. However, if the only way to find out the result of a certain action is to conduct an experiment, or in other words, to just do it and see what happens, that's complexity. And we have quite a few examples of complexity in our software engineering domain. For example, a trivial one. Have you ever worked on a code base which is so messed up that, you know, you're changing a line, you have no idea what's going to happen? And like best case scenario, you will find out what's going to happen immediately. Worst case, you're going to find out like a few months later in production. Well, that's complexity. Another example is when you have to implement a new feature or functionality, and well, it's really hard to understand what parts of the system have to be modified in order to accommodate that new requirement. That's a complexity as well. Now, another important question is what causes complexity? Because, you know, things, they are not really random, but what we are describing here is like almost random behavior. You know, quantum fluctuations, they're not going to affect the outcome of an if statement. If you pass the same input, it's going to generate the same output, right? But at the same time, well, we do face this uncertainty when working with complex code bases. So what is the source of complexity? What do you think? Any ideas?
You can yell them out loud. This is the interactive part.
Sorry? Null pointer exceptions. Yeah, what else? Number of dependencies.
Ooh.
You're close. What else? Indentation, okay.
Tabs versus spaces?
We are not starting religious wars here, please. What else? Sorry? What the fuck per second? Okay, you're really close. Okay, so the thing is, complexity is not only about the code itself and the design of the system, but it's also about us. In a sense, complexity is in the eye of the beholder. You know, we have our cognitive limits for processing information. Like, there was a study that was conducted in the 50s that concluded that we have mental capacity of 7 plus minus 2 information units that we can process. Then they repeated that study like 50 years later. This time the result was 4 plus minus 1. And interesting what's going to happen in another 50 years. Anyway, you're right. When we reach that limit, we start generating those what the fucks per minute. Anyway, to address complexity in software engineering, we have design patterns, we have architectural styles, methodologies, frameworks, etc. But the topic of this conference is, of course, metrics. Now, as we mentioned in the introduction, well, I have some complicated relationship with software design metrics. There was a time when I was really trying to be this metrics cop, trying to enforce different values using CI pipelines, etc. We were trying to reach out goals based on cyclomatic complexity and different ways to calculate coupling. But instead of leading us to a more maintainable and evolvable code bases, we ended up with a major disappointment, to be honest. Now, let me show you why. So let's say we have this abstractness metric. And in simple words, it's just a ratio of the number of abstract types to the overall number of types in a module or a package. Now, if you prioritize chasing a certain value for abstractness, you know, it's really easy to add abstractions. Like, come on. If the abstractness is really low, we add another abstraction. But does this number say anything about the quality of that abstraction? Not really, right? And we know that a bad abstraction is more expensive than duplication. So remember what Sonya said about unintended consequences? Well, here's another example. By adding ineffective abstractions, we are increasing complexity of the code base. Another closely related metric is called instability. And this one is brought to you by people who really, really hate ESL speakers like I am. Because this one is based on comparing efferent and afferent coupling. I really hope I pronounced it correctly. In simple words, it's just about comparing the dependencies that your module has on other components and the number of dependencies other components have on your module. So the higher this ratio, the more unstable your module is, meaning that it's more prone to cascading changes coming from other parts of the system. Now, let's say an example. Say we have this module in the middle, and other 10 modules depend on it. However, our module depends only on one external component. If we run the numbers through that metric, we'll get 1 divided by 11, and that will give us instability value of 0.09, which is like really great. It's almost 0. That means that our module is supposed to be really stable. It should really be protected against changes coming from its environment, right? Not really. The devil is in the details, and again, this metric misses those important details. I didn't say anything about how that single dependency was implemented. And in this specific case, it uses reflection to work with private members and methods of some external component. The authors of that external component know nothing about that integration even taking place. So every change they make to the implementation of that component, all of them have the potential to break our integration and cause cascading changes. But hey, we are really, really low on that instability scale. Another metric that combines the previous two is called distance from the main sequence. And this one simply means that a module should balance its stability and abstractness. The higher the abstractness, the more stable it should be. Now, although, of course, I do agree with the idea of what this metric aims to achieve, well, I can't trust the means because, well, those calculations, they're problematic. You know, if you hire creative engineers, they will find creative ways to get to the desired number in every metric. But that doesn't say anything about the complexity of the code base. So I wanted to formulate a more pragmatic, accessible, and easier to understand approach to evaluating complexity of code. And that led me to do something that I consider very, very, very stupid, and that's writing a book. It's called Balancing Coupling in Software Design. It was supposed to be published like a year ago, but hey, being bad at estimates is a part of our job, so don't blame me for that. Today, I will give you a preview of this book. But before, I want to ask, who here has already got my previous book, Learning Domain-Driven Design? Raise your hands. Okay, we have a couple of hands. All of you with hands down, you know what you have to do, right? I don't have to say it aloud. Mm-hmm. We are good. Okay. So let's get back to complexity. So we want to identify design decisions that are increasing the cognitive load on whoever is going to maintain the code base, and as a result, increase the complexity of the code base. Now, let's assume we have two components here. Any two components, and they're connected somehow. It doesn't matter the direction of this relationship. It can go either way, not important. It's also not really important how they're integrated. It can be synchronous or asynchronous. Also, let's stay with this abstract definition of a component. It can be a method in a class in a library, a module, a service, or a whole system. These can be two systems working with each other. And I don't want to define any specific levels of abstraction here because complexity can happen at any of these levels. Now, when the two components are connected, they're naturally exchanging some data. That data may describe, for example, the state of the data of one of the components, or it may communicate intention, what to do, a command that a component should execute. But that data, it's not really the most important part of the integration, at least in our context, when we want to evaluate complexity. There is something else that is being exchanged between these two components. Anybody here want to take a guess what that is?
Yell it out. Another interactive part. Everybody's still awake.
Yeah, come on, give me some ideas. I cannot hear you.
Comments?
Comments. No, let's consider that.
But we should always write comments.
Yeah, like tests. What else? Come on, Mark mentioned it.
Yes, actually. Thanks for stealing that. All right, I'll do it. It's knowledge.
Yes, that's knowledge. The more knowledge is shared between the components, the stronger they are integrated, and thus the higher the probability of a change in one component requiring a corresponding change in the second one. Now, we can categorize the knowledge that can be shared across component boundaries into 4 coarse-grained types: implementation, functional, model, and contract coupling. Let's see the differences between them. So First, as the name suggests, implementation coupling is all about knowing the implementation details of another component and using them for integration. In other words, a module ignores the public interface of another one and instead uses its private interfaces that were never intended for integration. Like we've seen a few slides ago, we can use reflection, for example. That's implementation coupling. Also, if you have a microservices-based system, and one of your services just ignores the public interface of another one, and instead just reaches out to its database directly, if that database was never intended for integration, well, that's implementation coupling as well. Now, needless to say that such integration method is fragile and implicit. The authors of the second module may even not be aware of this integration taking place, and thus every change has the potential to break the integration. We have to assume as if almost all knowledge is shared across components boundaries. Next, functional coupling means that the connected modules are sharing the knowledge of the business functionality they're implementing. Its practical implication is that the same business requirements are going to trigger simultaneous changes in both components. An extreme example of functional coupling would be two modules implementing exactly the same business rule or the same business algorithm. When that rule or algorithm has to change, the two components have to change simultaneously because otherwise the system is going to end up in an inconsistent state. A lower level of integration strength is model coupling. And this one means that the components are using the same model of the underlying business domain. For example, the model describes data structures and the terminology that is used to represent that business domain in code. When that model changes, again, the changes have to be propagated across the component's boundaries. And finally, the lowest level of shared knowledge is contract coupling. And here the components are integrated through an explicit integration-specific model that is decoupled from their implementation model, meaning that implementation can evolve independently of the integration contract, and thus it minimizes the knowledge that is being shared between the components, and it minimizes the chances of cascading changes between them. Now, if you're familiar with domain-driven design, then the published language pattern, it's a good example of contract coupling. Here, this one is an integration-oriented model that doesn't reflect any knowledge about how that component is implemented, its functional requirements, or the models that are being used there internally. Everything is encapsulated using this published language. So for evaluating complexity, it's important to identify the type of knowledge that is being shared between the two components. But that's not enough. Another crucial dimension is the dimension of space, or simply the distance, the physical distance between the components. And the thing is, the connections between modules can span different physical distances. These distances are usually closely related to what we call levels of abstraction. Knowledge can be shared between individual methods, classes, modules, submodules, components, microservices, whole systems. And the longer that distance between elements that have to be changed together, the more coordination effort is required to actually go ahead and implement the change. In other words, the cost of making a change is proportional to the distance between the affected components. And Sonya, I know that you have a good example of this.
Yes, though I don't know if I would call it good, but really exemplary. One of the teams I work with develops a customer portal. Customer portal needs customer data. Customer data lives in customer relationship management system. For some reasons that have been lost to time, customer portal doesn't get that data directly. It gets it through order management system. So what you have is your CRM system integration, order management system integration, and then customer portal gets it. So when the customer portal team needed just one more attribute of that customer data, I had to go hat in hand to two other teams, one of which completely didn't need it at all, and go, could you please change that for me and coordinate all of those deployments to make sure that the portal team gets it. So yes, that cost of change blew up because of the distance between those components.
Sounds fun. Okay, so now that we have these two quantities describing a relationship between two modules, let's analyze the possible extreme combinations and how they affect the complexity of the software. So let's start with the combination of low strength over high distance. So here the distance between the components is high, so we have high cost of implementing cascading changes. However, since the integration strength is low, this relationship, it balances distance out and it minimizes the chances of such cascading changes happening. So this relationship represents what we usually call loose coupling. Now the opposite, high strength over low distance. And here, because of the high integration strength, we have high shared knowledge and as a result, frequent cascading changes. However, the low distance balances it out and it minimizes the cost of implementing these cascading changes. The unrelated modules, they're like located close to each other, so when they have to be changed, it's almost like modifying one component. In other words, this relationship represents what we usually call high cohesion. Now, what about low strength over low distance? Is this a good one or a bad one? What do you think?
Louder.
A good one. Bad.
All right, 50-50.
Okay, cool. So let's analyze what's happening here. So because of the low distance, the cost of making cascading changes is low. But at the same time, the low integration strength minimizes the knowledge that is being shared between the components, and it minimizes the probability of cascading changes happening. So what we have here is two unrelated modules located close to each other. Now, assuming that usually it's not only two, but we can speak about dozens of them, that increases the local complexity of whatever module that is hosting them, right? Whoever is going to maintain or evolve that module, they will have increased cognitive load when they will have to change something. They see all this unrelated stuff and they need to find the specific thing they need to change. And it makes it harder to do that. So this relationship increases cognitive load. As a result, it increases complexity of the system. Now, the final relationship is high strength over high distance. And here the shared knowledge is high. So again, frequent cascading changes. And to make matters worse, because of the high distance, these cascading changes are also expensive. So here what we have is another type of complexity. This time it's global complexity. This relationship increases the flow of knowledge across the whole system, and it makes it more complex. I wanted to reiterate, local complexity is about the complexity of a single module, the complexity of its internals, and global complexity is about the interactions happening in the overarching module or system. Now, both types of complexity increase the cognitive load on whoever is going to maintain or evolve that code base in the future. So we have four options here. Where do we want to be? Well, I guess that's trivial. We want to be on the green squares and we want to avoid the red squares. Now, the red squares, that's complexity. This is the type of integrations that increase complexity of the system. Now, what can we represent using the green squares? Give me some ideas. One word to describe the two green squares. More ideas? Legacy? No, it's a good thing. Yeah, that's correct, but this is relevant also for other paradigms, not only object-oriented. Sorry? You are really close. Yeah. You are really close, so I won't torture you anymore. So, modularity can be expressed as strength, exclusive, or distance. One of them has to be high, the second one has to be low. If two are high or two are low, that's complexity. They have to balance each other. And we can compress it a bit to M equals S XOR D. To apply this in practice, always reduce integration strength as much as possible. And that as much as possible depends on your concrete case, because we have 4 levels of integration strength, but it's not always possible to be on the lowest one, because if you have 2 modules implementing closely related business functionality, nothing you can do about it. That's functional coupling. Also, sometimes you do need to use the same model of the business domain, so there is no way to get to contract coupling. Now, once you've got to the lowest possible strength, balance the distance. If both strength and distance are high, it will be easier to maintain that relationship if you bring those components closer, if you reduce the distance between them. If, on the other hand, both are low, you can simplify the design of the system by spreading them apart, by increasing the distance. Now, disclaimer, that was preview of this book. Hopefully it will be out early next year, I think so. That model, you can use it. However, the terminology may change when the book gets published. The book is going to include another dimension that I couldn't cover because of time constraints today. It will expand that S XOR D formula with additional dimension. The book will also provide more examples, and of course, in the book I will explain where this model where it comes from and how it relates to other means of evaluating coupling, like kinescence and structured design. And with that, back to you, Sonya.
All right, so don't need to read all the bullet points. We, in the business focus portion of it, we went over the metric that we would love to look at, which is business's ability to change and the software architecture supporting it in 2 dimensions, and those dimensions are change frequency and change effectiveness. And we also looked at how we can measure it with the 4 metrics that we were able to borrow from the world of DevOps, which is cycle time, deployment frequency, change failure rate, and mean time to restore. And along with it, realize that all 4 of those factor into the cost of change, which is proportional to the complexity of change. Now, Vlad gave us a wonderful overview of how shared knowledge impacts complexity, what types of shared knowledge are out there, and provided a really good compact formula for modularity and how to mitigate that complexity by using the factors of modularity, which is integration strength and distance. All right, so how are we doing for time? We have just a few additional materials to look at. Vlad's book, of course, when it comes out. If you haven't read the Accelerate book, I highly recommend it. If you want to look at more of a product evolution, take a look at orderly mapping.
Yeah, so we don't have much time for Q&A, but we'll be around. Now, O'Reilly are going to give us a few copies of the Learning Domain-Driven Design book. So if you want to participate in a raffle, talk to me or Sonya and ask us to scan your badge. We are not going to spam you. We have nothing to sell, so don't worry, just for getting information about people who want to participate in the raffle of this book.
All right, and with that, thank you so much.
Thank you.